Okay. So we're reviewing the web page for radiocarbon dating. And the way you know how to answer number 1 is it starts with how many protons does N14 and carbon-14 have. You don't need to know what any of this other information is. Just look at your periodic table. So I open my periodic table. I find nitrogen and its atomic number. That will tell me the protons. So if I zoom in, nitrogen has 7 protons, carbon has 6 protons. So because nitrogen 14 is first, that's 7 and 6. And we reviewed this in class, but also here talks about cosmic rays with N14 by blank. So N14 cosmic rays turn into carbon-14 by neutron capture. Down here, carbon-14 turns back to nitrogen-14 by beta decay. But because it asks for cosmic rays and N14 first, neutron capture has to be first. And if you're not sure, you won't be allowed to go to the next page until your answers are correct. So here are the 3 isotopes of carbon, which is most abundant, most common, and which is radioactive. Right here, talked about this in class. Carbon-14 is radioactive, so you only have 2 choices. But when you go back here and look, carbon-13, it says rare carbon-13. That means it's not found everywhere. So abundance is a lot or many. So we want carbon-12 and carbon-14. Just ask for most abundant first and radioactive last. So we don't want this one because it talks about most abundant first. And this one, when you have something in a percentage and you're taking it out of a percentage, you divide by 100. This would add 2 more zeros in front of the 1. So then if you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you have 1 times 10 to the negative 10th. Add on 2 more decimal places, that's 1 times 10 to the negative 12th. Or 1 to the 12th is 1,000 billion or 1 trillion. Yes. After death, the amount of carbon-14 begins to decrease. True. Which of the following materials cannot be dated by this method? So when you go back and look, it's asking about carbon-14. So it has to have been living at one point. So bones, wood, pottery with charcoal. The charcoal has carbon in it. And your soil also has carbon in it. It's because some of those pieces of wood and bone break up and turn into soil over time. So all of this you could date with carbon-14, except volcanic ash. And if it doesn't show up, just click allow. So this is an interactive graph. This purple stuff is your radioactive carbon-14. As it decays, so we have 100% radioactive carbon-14, 100%. This HL stands for half-life. So each half-life, the amount reduces by 50% or 1/2. So after 1 half-life, it goes to 50. Half of 50 is 25. Half of 25 is 12.5. Half of 12.5 is 6.25. Half of that is 3.125. But notice they don't have all the decimals, so it's rounded to 3.13. This is probably 1.5625, et cetera, but they just round it to 2 decimal places. Okay, and if we move this bar, we're gonna draw our line on the graph for us. Or I should say the computer's gonna draw our line. So this is at 1 half-life, we had 50%. 2 half-lives, we had 25%. And notice there's less in this box. 3 half-lives, 4 half-lives, 5, 6, 7, 8, 9. So it's getting close to 0, but it will never reach 0. It just keeps getting smaller and smaller, more decimals. So we're going to use this information in the chart and the graph to answer the questions below. So you should pause the video. And I'm going to pause the video before you check the answers so you can answer the questions. Okay. So these are your answers, because for 3, if you read above, it says the daughter product N14 is not retained by a specimen because it is a gas and escapes as it forms. As soon as it forms, it escapes. And this is actually the wrong answer. I know a lot of people are thinking, oh, but if I divide 0.2 by a half, if I cut it in half, that's 0.1%. But they want this fraction. So this would be 1 over 1,000, because 512 times 2, or 1 over 512 times 1 over 2, is really 1 over 512 times 2, which is 1,024. So it has to be less than 1 over 1,000. And we are correct. Okay. So this has lots of information in it. And I'm just going to read the top so I understand what I'm looking at. It says the half-life of carbon-14 is 5,730 years. A sample that is decayed for 3 half-lives is 3 times 5,730, or 17,190 years old. To determine how much carbon-14 is in a sample, radiation detectors count the number of beta particles released by radioactive decay. The result is called the activity, or disintegrations per minute per gram of carbon, DPM per gram, is how you pronounce that. Sorry. Modern samples have an activity of about 12.5 DPM per gram. Older samples have values less than the modern value. So carbon-14 measurements are often expressed as percent modern, which is the ratio of sample activity to modern activity. For example, a percent modern value of 25% means that the sample contains 25% of its initial carbon-14, or 25% of the parent atom. The sample size required for this method depends on this type of material, but is generally in the tens to hundreds of grams range. Very small samples just don't have enough carbon-14 to be reliably measured. The smallest carbon-14 activity measurable with most methods is about 0.2% modern, which corresponds to about 9 half-lives. So we can't use these methods for 10 or more half-lives. Okay. Drag your mouse pointer on the red dot here to see how carbon-14 remaining and half-life are related, with 60% parent remaining, half-life, move this so it's close to 60%, or 61.6%, it's a little over 0.7 half-lives. Use the carbon-14 decay curve and the calculator to help you answer the study questions. The calculator has the half-life of C14 built in and allows you to convert fractions of half-lives to years. For example, a sample with only 90% residual carbon-14 is about 0.16 half-lives. So if I go up to 90, .1, 0.2, but it's telling me that if I type in 0.16 and hit enter, I should be around 900 years. So about what percent of modern C14 remains in a sample that is 2 half-lives old? So I want this to go to 2 half-lives. And that looks like 25%. What about a sample that's 5 half-lives old? So half-lives are on the x-axis, 3.1%. I'm going to choose 3%. What is the approximate age of a sample that contains 90% of its original carbon-14? It just told us up here, it's 900 years. What is the approximate age in years of a sample that contains 30%? So I'm going to make this percentage as close to 30 as possible and type that half-life number into my calculator. So I'm going to do 1.7. 9741. So 9,700 is closest to that number. What is the approximate age in years of a sample that contains 3%? Well, from question 2, 3% was around 5 half-lives. So do 5. And that would really, in your calculators, be 5 times this number. Should be around 28,000, just rounding to whatever's closest to my number. And then it says 0.2% is the smallest activity that a sensitive detector can measure. Using this value, what is the approximate age in years that can be determined with the C14 method? Well, it told us up here that, where was it? No, up here it was. The smallest carbon-14 activity measurable with most methods is about 0.2% modern, which corresponds to about 9 half-lives. So I'm putting 9 in here. And that's 51,000 or 52,000. If I check my answers, I'm good. Now this page also requires some interaction, but we need to read how to interact with this. So before we plot up real data to compare with the theoretical decay curve, let's see how years are reported. Dates can be expressed as AD, BC, or BCE, before Common Era, and BP, before present. The accepted way to represent carbon-14 ages is in terms of BP, where the year 1950 is used as the present. 1950 is a date that the calibration curves were established. It also predates atmospheric testing of the atom bomb, which significantly upset the carbon-12 to carbon-14 ratios in the following years. The timeline on the right illustrates the relationship between BP on the bottom, BC, and AD. Click on the image and draw it back and forth to study this relationship. Below are descriptions of 6 samples with known ages expressed as either AD or BC, also called BCE. Convert these dates to BP dates using 1950 as the present. Also convert the 3 estimates of carbon-14 years in the second table to BP dates. Here's the second table. So Douglas fir tree rings excavated from a cave in Arizona, date 577 AD. So I'm going to move this until the top is as close to 577 as possible. So I had 570 and 585. So I'm going to type in 1380. Oops, I'm sorry. It says 1373. Most probably because 585 is 1365. Okay. And then if you realize 577 to 585 is 8. So if you add on 8 to this, you end up with 1373. Okay, now I want to do 200 BCE. So I'm going to the other set of 0 to 10 is 2160. So if I do 2160 minus 10, well, if I go to 225, the number is going higher. So if I go to 195, the number is getting lower. So I'm going to subtract 10 from this. So this is really 2150. Okay. I'm going to pause the recording so you can practice some of these. So the next one says 675. It gives me it exactly. 979 BCE. So I'm going to just see if it'll take my 2925. And you can always check your answers here by clicking next. And it says 4, 5, 8, and 9 are wrong. Okay. Okay. So 79, the number is going up. So I need it to go up by 4. Let's see if it takes that. Now it likes 4. And this is BC, so 1843. So I want this top number to be 1843. $18.45 is 33795. Okay. So it's 2 years off. So let me do 3795 minus 2, 3793. It likes that. Okay. Then on the bottom, assuming this is 1999, convert these ages into BP dates. Example, an article that's 1,000 years old has a BP age of 951. So the age on here minus 1999 minus 1950. So if the BP, an article that's 1,000 years old, its age is 1,000, minus 1999 minus 1950, you get 951. So this was 4731. So the age is 4,731. Because I can't go further back than that. So if we do 12 to 00 minus, so essentially we're doing 1999 minus 1950, right? That is 49 years. So I'm just subtracting 49 years from these things. So that's how they got 4682 here. So 12,200 minus 49, or 200 minus 49, is 12,151. And it likes it. Okay. And then 906 minus 49. Instead of 851, it should be 857. Yay. So now we're going to plot these points over here. This is percent modern, and this is the time in years. So my percent is 76, and my age is 2160. So 70. Oh, and you'll know you're in the right place when it just goes blue when you let go of it. This is 73.4%. 69.4%. 63.8%. And 56%. Okay. And then you want to screenshot this to put on your document. So when you screenshot it, make sure it saves down to your drive instead of copy to clipboard, because you can't insert it into Cami unless it's saved. Now, before applying the carbon-14 method to some newly discovered materials, you need to examine one of its assumptions, that the amount of carbon-14 produced in the Earth's upper atmosphere from cosmic rays striking M14 is constant over time. It turns out that the production of carbon-14 changes somewhat from year to year because of variations in incoming cosmic radiation. Increased solar flare activity increases carbon-14, with higher amounts of carbon-14 found in organisms that lived during those times. To compensate for variations in carbon-14, scientists have developed calibration curves from studies of tree rings of the ancient bristlecone pines of the White Mountains of California and oak trees of Germany and Ireland. Through these studies, called dendrochronology, that came out really bad, dendrochronology, calibration data has been developed that goes back nearly 11,000 years. The applet below compares actual tree ring ages from counting with the equivalent radiocarbon age. Use your mouse to drag on the wood core to set the variation in tree rings between 1,000 and 400 years. So notice the actual age is here and then the carbon-14 age. So then you answer these questions. And I'm going to pause recording while you answer those because I think this is fairly straightforward. You're just moving this around until you get your answers, and you can always check your answers quickly. All right, hopefully you made it. Use the findings of tree ring research. It's possible to adjust radiocarbon determined dates to correct for variations. So we're going to adjust using this graph. So if we move this dot around the curves, so that we can see our line, our red lines are what was expected. Our blue lines are what is the actual. I'm sorry. The red line is what expected. The black line is actual. And then the wherever it hits at the top is the corrected age before, and at the bottom is corrected age AD. For example, 400 to 1,000 range, a radiocarbon age of 800 years has a corrected age of only 600 years. So, and also as you change these, you are able to zoom in on different parts of the graph to get a more accurate corrected age. So use appropriate correction curve to convert a radiocarbon measured age of 1450 BP to the corrected BP. So we want this side to say be in the range of 1450. So we can use this one, but notice it's hard to figure out whether you're at 1450 or not. Whether that's here, because it starts at 1400. So maybe this is 1450. And the actual age, BP, sorry, is here 1800. Not an option. So let's go down to this one. Oh, that's because I slowly put it here. So 1450 is here, and I want to cross the black line. It's really 1400. And you can check that on here. So if you go here to 1450 on the Y, it corrects to maybe 1200 or 1250, which is also not an option. Let's see if it likes this answer. Nope, it says 1, 2, 3, and 4 are wrong. Oh, that's because that doesn't go down far enough, but 1450. Oh, was I checking? I was checking it. Like 1350 for some reason. So we want 2700 BP. So it's definitely in this range. If it's not 2800, then it's going to be 2850. I liked it. The modern day burning of fossil fuels there's more carbon-14 in the atmosphere, it will make them appear younger if we don't have a correction curve. Nope. Older. Or it will be impossible. There we go. Be impossible to determine without a correction curve, of course. So you want 2225 years. So we have this dip. So they should seek other information or use an average. Seek other information. So you're almost done. And I have to stop.